today I'm going to cover the second order, basically the second order optimization. So last time, Jayon covered the first order. If you have any problems after that, you can still ask me during this. So the quadratic programming, basically we say that we have a objective function that has, you can see that this is second order because we have a W transpose and another W adding together in a function. So the whole thing is basically we try to minimize the one that on the left, and we have some constraints on the left, on the right side. So usually we define this very clearly as Q is a symmetric matrix and W C equals in a real number space. And we have our A, which is also a real number space, and B. So we have all these, so it is very hard to see it this way. But if I give you a very simple example in the later, you will actually feel that this is what you will encounter in your everyday life for your research. So basically we're saying that we have a objective function on the left side. So it is like the circular thing. And you have this constraint on the right. It looks like a plane. So you're trying to find the intersection between them in order to find the optimal solution. So here is a very simple example. So if we say convex optimization, here Q is a positive semi-definite, which means that when we do this X transpose of Q and X, it has to be a positive number for any X. So the object function is convex. So this is actually convex optimization is what you encounter very often in real life. So you use it very often for different reasons. For example, like in chemical engineering, in MECI, you all need to solve these functions. So we say we want to find we say we want to find a W that exists that could give you a local minimizer for the global. So definitely we have some simplified version. If the Q equals to 0, then it reduces to linear programming problem. And when we say we try to solve in general QP, it is a NP hard problem. But sometimes, mostly, we would encounter some very nice polynomial time solution for the convex QP. Here is an example. So it is very simple. You can see that we have this function that we want to minimize on the left side. So and the some constraints on the right side. So we can see that we said that the optimization function is like this. So it is the half of the W transpose Q and W. So if we go to this example, we can simply calculate it. So if you do a simplify, you can simplify the right side by making everything out, and you can do it equals to x quadrant and then y quadrant, and then it's 64. So it's on the left side. You can see there is you ignore the constant on the right, and then you can see that it equals to Q equals to 2 and 8 on the diagonal side, and the other side it's 0, 0. So it's positive semi-definite. So anybody knows how to do this simple calculation? If I can walk you through it, but it's very simple. So basically, on the right side you can see A, which is you can see the constraint is x plus 1 because it's smaller than 7. So it is very simple. A, when you multiply by x and y, you get smaller than b. So when you're going to do a very simple solution, you can use MATLAB. There is a program that you can, a function that you can call. It's basically just a simplified version we call it clock program. So this is a very simple example. I would say that this is the start for you to look into this kind of complex optimization. It is something that you can do by your hand, but definitely there are more complex examples, so you have to do it by calling certain functions. So did Alex cover support vector machine in the class? Okay. So the support vector machine is the most popular classifier right now. It is simply the function, I already wrote it out here. It's that you want to do it's basically a quadratic programming problem if you see it this way. So it is, the support vector machine is trying to maximize the margin between the two classes. So if Alex didn't cover that, how many of you know support vector machines? I think it's have you ever solved a support vector machine classifier? Have you used liblinear or any liblinear? It's the most efficient way of implementing things. I can explain a little bit. For support vector machine, it's a very popular method. I think Alex will cover it again. Let's see. So I think Alex will cover it in details. So I'm just gonna go over a little bit so that I can jump to what I want to do. So it is so we frame it as a classification problem. There are red dots and there are gray dots. We try to find a margin, a line to separate them. So we want to say